Hi and welcome to another chemistry lesson. We're looking at acids and bases, and specifically we're looking at pH. Okay, pH is what? Okay, well, pH is a measure of a solution's acidity, or would we call it basicness? I don't know. I think the other word is better. Alkalinity. Okay. In other words, pH measures if a solution is acidic, and how acidic is it, or if a solution is basic. Okay, so what it is not, and I think many people misunderstand what pH is. What it is not testing how strong an acid is. Okay, it is testing that if I add if I have water and I add a substance to it, okay, does it make water to be acidic, or does it make the watery solution to be basic? Now, what makes the difference? Well, it's all about the concentration of hydrogen. Okay, if we add a substance to water and it increases the concentration of hydrogen, it means that it is acidic. Okay, if however we add it to water and it decreases the concentration of hydrogen, okay, then it means it is a basic solution. Now, the more acidic it gets, the more the solution actually becomes a stronger acid. Okay, yes, that does mean that. And the more it decreases the concentration of hydrogen, the more the solution becomes a strong base. Okay, so but with that in mind, let's just quickly look at why pH. Why is it called pH? It's actually very simple, because the P in pH always stands for negative log. Whenever you see P in front of a constant or value, you know it means take the negative log of that value. H just represents the concentration of hydrogen, so that pH is quite literally not a formula, it's literally negative log of the concentration of hydrogen. Okay, now since water is the starting point, we are literally taking water, adding a substance to it, calling it a solution, and then testing whether the solution is acidic or basic. Let's look at water itself. If we just take water and look at this dissociation of water into its ions, we see that water dissociates into hydrogen, okay, sorry, without that bracket, okay, into hydrogen and into hydroxide ions. Okay, with the water obviously being a liquid, ions being now in a solution, so they're aqueous. And notice that this is a reverse reaction. In other words, at some point it reaches equilibrium where the dissociation, the forward dissociation and the reverse production of water is equal. And because it can reach equilibrium, we can work out an equilibrium constant. Okay, there's practical experiments to work out this constant. And now what's interesting, remember the equilibrium constant, and the W just stands for water. The equilibrium constant for water does not have a denominator, or the denominator is 1. The reason for that is we have the concentration of products. You might recall that. This is how we get concentration of products divided by the concentration of reactants. This is how we get the equilibrium constant. But the elements must either be gases or aqueous elements in the reaction, and therefore there are no reactants that are gases or aqueous solutions. So we only have that this is hydrogen, concentration of hydrogen times the concentration of hydroxide. Okay, now very important, the reason why water forms the base of, not, I shouldn't use the word base, it has a different meaning here, isn't it? Okay, but the reason why water forms the starting point is because in water our hydrogen concentration is equal to the hydroxide concentration. Okay, so that is a very important fact about water, and the reason why we call water the neutral. So water is neutral. When we increase the concentration of hydrogen in water, we make an acidic solution. If we decrease the concentration of acid, that literally means to decrease this, since the Kw value is a constant, remember that. Okay, if we decrease this value, we will increase that value. Okay, so, and according to Arrhenius, the definition of an acid is something that increases the concentration of hydrogen, and a base is something that increases the concentration of hydroxide. Okay, so hopefully you are getting my drift at this point. Now the only other thing I need to add here is that in experimental evidence has shown that the Kw value at standard conditions, for example 25 degrees Celsius, okay, the standard conditions produce a Kw value of 1 times 10 to the power of negative 14. Okay, it's actually 1,008, but we'll work with 1 just to keep it simple. Now Kw itself is a constant at standard conditions. At higher at higher temperatures, this value changes. I can't remember now if it increases or decreases with increase or decrease in temperature, but we do recall that the only thing that changes the equilibrium constant is temperature. That is the one thing that I can change that changes the Kw value. Now if that value changes, it doesn't change this fact. Okay, so just because Kw maybe isn't 1 times 10 to the power of 14 doesn't change the fact that in water hydrogen and hydroxide concentration are still the same. If we increase the temperature, it will just shift the reaction to the left or to the right, depending on whether this is an exothermic or an endothermic reaction, and that causes the change in Kw, but it doesn't change the fact the concentration is still the same. Okay, it will still produce the same increase here as it would produce an increase there, keeping the concentration the same. And this is why water is neutral. Okay, it doesn't have an excess of the one or the other. Okay, I think I've emphasized that quite enough, so let's go on from here. So using these two values, let's see if we can go and work out the pH of water. Okay, you immediately might say the pH is 7. My question is why? Why is the pH of water 7? Where does that come from? Well, let me show you. It's very interesting. Okay, first of all, we know that this is true. Okay, and we know that this is true. So if we know that the concentration of hydrogen times hydroxide, hydrogen times hydroxide is equal to 10 to the power of negative 14. Forgive me for leaving out the 1, but you can see why. Hydrogen times hydroxide equals 10 to the power of 14. Why am I refusing to write hydroxide? Because I want to replace hydroxide with hydrogen. Okay, they're equal. If whether I take the concentration of hydrogen times hydroxide or hydrogen times itself, since hydroxide is equal to hydrogen in concentration, I might as well substitute it there. And the reason why I do that is because I actually want to solve. I want to see what is the concentration of hydrogen in water. What am I doing there? That should be a square. Should be 10 to the power of negative 14. Okay, now to solve this, and I am first of all a mathematician, so I love this part of chemistry. Take the square root on both sides. I'm supposed to take a plus minus on this side, but the reason why I don't is because negative concentration means nothing. Okay, so I will keep it positive. And when we take the square root of a base and exponent pair, we would divide the exponent with 2. Okay, so hydrogen is equal to 10 to the power of negative 7. You could have seen it, yeah. If hydrogen squared is 10 to the power of 14, negative 14, then hydrogen itself must be 10 to the power of half of 14. Okay, so this is literally the concentration of hydrogen. In other words, if we look at concentration is equal to N over V. That represents the how we calculate concentration of a solution. Then per volume, the moles per volume unit is 10 to the power of negative 7. Okay, now that enables us to work out pH, because P is negative log H is the concentration of hydrogen, which is 10. Let's just get rid of that square bracket. The square bracket is only there to demark the fact that I'm working with concentration, 10 to the power of negative 7. If you know your log laws, you know that negative 7 in logarithms, if I have a negative 7 exponent or an exponent inside the log, I can multiply it to the front. So I've got negative 1, there's a negative 1 in front there, times negative 7, which gives me 7. And then log, this is a base 10. Since the base and the interior, the input is the same, that gives me a 1. And therefore this is 7 times 1, which just gives me a pH of 7. Now again, this is at standard conditions. This is at 25 degrees Celsius. At 25 degrees Celsius, at standard conditions, 7 is a neutral pH. In other words, if I measure something and I measure a pH of 7, it will tell me it's a neutral solution. It's neither acidic nor is it basic. Okay. However, if temperature increases or decreases, and again I can't remember which one is which, we might have something like 7.5. We measure the pH of water and we get 7.5, or we get 6.8 or something like that. Does that now make water an acid all of a sudden? No, it changes what the neutral pH is. At different temperatures, we might have different values to be the neutral pH value. Okay, so just keep that in mind. It's not a big thing because you will mostly be working with standard conditions, okay, but it helps in understanding where all of this comes from. Okay, so now let's go and have a look at well, does a value less than this mean it's acidic or basic? Does a value more than this means it's acidic or basic? And to demonstrate it, I want to use a graph to demonstrate it again, just because I love adding maths into this whole process. So let's do maths and colors. That might keep your attention. Okay, so we draw our graph on this axis. Okay, and I'll start by just drawing for you the standard logarithmic shape. So if I draw a logarithm, if I draw the normal log, this is my y values and these are my x values. So the normal graph y is equal to log of x, okay, will look like this. Roughly, it will look like that. Actually, let me draw it a little bit more to this side so I have space. Okay, this would be my normal log value, y is equal to log of x. If I now draw y is equal to negative log of x, that's the important one I want to work with. Why? Well, because I'm trying to get pH. Where's my pH defined? pH, there we go. I want to draw this. I'll bring all of it together hopefully in a minute, and then you'll understand why am I frustrating you with maths. But here we go. If I draw y is equal to negative, and actually I must, what we do with this graph is we reflect it in the x-axis. Okay, so whenever the y expression, this was the y expression, gets multiplied with a negative, it gets reflected in the x-axis. And I'm going to try and do it nicely. No, it's not working. Let's go this way. Okay, there we go. Okay, so I'm reflecting it in the x-axis, and it looks roughly something like this. So for now, I'm going to ask you to ignore the original log. Okay, so please ignore that one. And what we do know is this value is 1. That value where it cuts is 1. In other words, if my x value is 1, the y value will be 0. So this is the coordinate 1, 0. Now, what I do want to do though is I just want to change this. Instead of working with y's and x's, because that's not what we're working with here, we're working with the pH. So we have pH is equal to negative log of the concentration of hydrogen, which means if I look at that, it just means that this value on here is pH, and then this value on the horizontal axis is the concentration of hydrogen. And then we saw at negative, at the value now, it is much smaller than that, so forgive my graph is definitely not according to scale, but at 10 to the power of negative 14, okay, that if that is the concentration of hydrogen, we saw it here, if that is my x value, my input value, then my output value is 7. Okay, so the scale on here would be that if I go here, I find my concentration is 7. Okay, that is my hydrogen solution. So remember now that hydrogen itself is also a product of, if I have hydrogen, let's go back here to show you that. If this is true, this part is true, then it means that hydrogen hydroxide is equal to 10 to the power of negative 14 divided by the hydrogen solution. Sorry, hydrogen concentration. So that if hydrogen increases, if this value increases, it's the denominator of a fraction which decreases the fraction itself. Okay, so therefore if hydrogen increases, hydroxide decreases, or if hydrogen decreases, the denominator decreases, it increases the fraction, which means that hydroxide is increasing. So just keep that in mind, that even though on my horizontal axis I have hydrogen, it also indirectly refers to the hydroxide concentration as 10 to the power of negative 14 divided by hydroxide, it's hydrogen. Okay, now I say this because I want to show you now what does the effect of an increase in hydrogen have on pH. Look at this. So if this is the standard solution, now or the pH of water at standard conditions, if I add something to water and I now measure the concentration of hydrogen and I find that the concentration has increased. Increased means I'm going to the right on here. Notice what happens if I go to my graph and I go to the right. Now I have a decreased value. Okay, so again, the maths behind this is a sloping down graph. So as I go to the right, my y values go down. So notice the higher I go, the closer I go to having a concentration of 1. Remember, this is the x value 1, or the hydrogen equal to 1 would be that position. If the hydrogen concentration is 1, it means my pH value will be 0. So anything less than 7 would be acidic. Okay, anything less than 7 would be acidic. Why? Well, because it represents a pH less than 7 represents a hydrogen that is less as or hydrogen concentration that has increased. Okay, does that make sense? So anything on this side. Now the same goes for decreasing the hydrogen concentration. Okay, so if hydrogen concentration is decreasing, it means hydroxide is increasing. But let's just look at what happens. So this is increasing, okay, sorry, decreasing hydrogen, I'm now less than 10 to the power of, not negative 14, sorry, that's been there for so long, okay, negative 7, forgive me, okay, so if hydrogen decreases, concentration of hydrogen decreases, notice the pH value is increasing the closer I get to 0. As a matter of fact, if I get to 0, I'll be at infinity, okay, so this just goes up and up and up and up, so that if I have a pH that is greater than 7, I would be working with a basic solution, okay, a solution that has more hydrogens than hydroxides, and the bigger that gap, the more basic the solution would be. Does that make sense? I really do hope that it does. Okay, so now just one more thing. We know that the distance now between here and here, that would be 7, okay, and so if we take the same distance from 7 to the top, that would be 14. Okay, so we usually work in a range between 0 to 7 to 14, but that does not mean this is the limit. These are the limits for pH. That is a common mistake. pH does not go between 0 and 14. pH can even be negative, okay, you can have negative values. You can't have a negative hydrogen, okay, concentration. That's why we don't work with a negative axis, but we can have negative pH if my concentration is more than 1. The fact of the matter is we just very seldom work with such acidic solutions. I mean, it's very rare to get such an acidic solution, so that it is practically a limit. 0 is practically a limit for acidity. But for example, battery acid. Battery acid is water and is an acidic solution, and it has an acidic solution of almost -1. So I mean, 0 is not a limit, it can be negative. Okay, the same with 14. The 14 is not the ultimate basic solution. 14 is just a practical limit. Most, if not almost all, of our solutions will be 14 or less than 14, but it could be more. Okay, there's nothing that stops it from being more, because if we can decrease the hydrogen to be less than 10 to the power of, what would it be, -14, isn't it? Okay, then we will have a pH that's less than 14. Okay, so just to quickly recap, pH is a measure of a solution's acidity or basicness or alkalinity, and it always involves water and testing whether a water is has an increase in hydrogen or an increase in hydroxide. pH is calculated by taking the negative log of hydrogens, and we use water as the starting point. Water under standard conditions will have a pH value of 7 under standard conditions, but it can be less and can be more if we change the temperature. Based on that 7, if we find the pH of a solution to be less than 7, it means that a solution is acidic. We added an acid to the solution. If that solution is greater than 7, it means that solution is basic. So that our range for pH is usually between 0 and 14, with 7 the neutral value, meaning that at 7 our hydrogens would equal our hydroxides. Less than 7 hydrogens would be more than 7 hydrogen would be less. Other than that, I will let you go, and I really hope you enjoyed and you learned something about pH, and I'll see you in the next video. Hopefully in that one I will look at indicators that are used to measure the pH of solutions. We'll see you there.